to explain you the concept that is at the base of the formulation that we developed, we don't know what causes the degradation of the tissue, but we are sure that the tissue starts to degrade. When the tissue is degrading, the intraocular pressure is still acting. So we thought that probably, we hypothesized that there's some sort of structural volume rearrangement that from the normal direction of the cornea moves to the tangential direction. So we hypothesized an in-plane growth and out-of-plane thinning. All this process is driven by the strain. What do I mean? Of course, as I said, we have some sort of degradation of the tissue. If this degradation actually causes an increase in the strain, the growth process will be triggered. I didn't put here all the equation of the formulation, but if you want to know more, we just published this August the paper on it, so if you want to have a look, scan the QR code. And okay, what we actually control is the degradation, but we cannot control the growth. That is, we cannot control how the cone will appear or the shape. So we defined a space-time dependent degradation function that controls the loss of the properties of the tissue. And this degradation was applied to the extracellular matrix, to the fibers, and also to the loss of the orientation of the fibers. As we can see, the degradation begins from the posterior surface and slowly diffuses towards the anterior, but also the transition zone between the pathological zone and the healthy zone is increasing throughout time, as the pathology worsens, of course. And we did the same, as I just told you, with the direction of the fibers. So the fibers in keratoconus deorganize, breaks, lose the orientation, and so this is not working well. Oh, okay, it's going only one. Well, okay. The simulation is quite simple. So we recover the stress-free configuration that is the cornea without the intraocular pressure. We apply a physiological value of the intraocular pressure, and then the degradation starts. If the strain increases, also the growth of the cone will start. Otherwise, nothing will happen. So we wanted to analyze the influence of the effect, the influence of the position and the dimension of the pathological zone on keratoconus development and progression. So we considered two scenarios, a centered pathological zone and an off-centered pathological zone, and also different dimensions of the degraded area of radius 1, 2, and 3, plus the transition zone that is increasing throughout time until reaching the double of the value of the radius of the pathological zone. So this map that I'm showing you, basically the colors represent where the tissue has grown more. So red, it has grown a lot, blue, it didn't grow. This is the center cone for different dimensions that we obtain, and this is the off-center case. What is important here is we noticed that the position of the pathological zone was not highly influencing the final cone shape that came out, that resulted, but what was important was the dimension of the pathological zone. If we look at the cones with radius 2 and 3, we see that the growth was more homogeneous. It's basically very symmetric. This is due to the fact that if the pathological zone is the degraded zone in keratoconus is quite big, the extracellular matrix cannot stand anymore to sustain the overall corneal geometry, and so it collapses basically. While for smaller cones, we have a more heterogeneous growth due to the fact that the extracellular matrix is still playing a role, even if there's a small region where he degraded, he lost these properties. So, also we wanted to evaluate the severity of the cones that we obtain, and we computed the Belling grading system as it is done in pentagram topographer, and I want you to center your attention on the thinness bathymetry. At the beginning, the eye was healthy and it had a central corneal thickness of 564 micrometers. And we obtained a bathymetry thinning of 162, 223. That is our most important result that we obtained with this model. So, we with our model, we can track the progression of the cone. For example, these are the pachymetry maps of the different cases of the three cones, of the three keratoconus that we considered for the off-center case. And as we can see, when the simulation has not started yet and the tissue is healthy, the pachymetry is very regular. But as soon as the tissue begins to degrade, the growth begins, and so also the thinning phenomenon. And another thing that, in the center of the thinnest point, this places toward the center of the pathological zone. Another thing that we notice is that the bigger is the pathological, the affected area, the worse will be this thinning phenomenon. And this is just to give you an overlook from a qualitative point of view of what our model does. So this is just a section, but our model is actually 3D, so it's the whole cornea. And as you can see, it reproduces quite well different kinds of shape of keratoconus. So just to resume what we just saw, the formulation is able to reproduce keratoconus growth in terms of bulging and thinning, and the dimension of the pathological area highly affects the final cone shape. Current limitation, of course, there are limitations in this work, and this is that we applied one-way coupling between material degradation and corneal growth. What do I mean? That the degradation is actually influencing the growth, but the growth is not influencing the degradation. So we would like to add this aspect. And also, patient-specific data were not included yet, but we plan to do it thanks to Professor Zahabi that gave us some data. I know that this is not trivial at all, because every keratoconus is different, but we will try somehow to reach some sort of validation of the model. So, to conclude, I would like to thank Professor Calvo and Professor Rodriguez that guided me through the whole process, and thank you for the attention.
Okay, Benedetta, thank you very much for your nice presentation. Any questions for Benedetta?
Thank you for your presentation, it was very nice. Benedetta, just one comment, it's not simple. You said that it's very simple simulation. It's not, you make a lot of work. And just I wanted to ask about the boundary condition, which you assumed.
Yes, I mentioned them, but they were not like very underlined. In this case, I just fixed the base. So I fixed the base of the limbus. It's fixed.
Okay, and so many...
in this, here, all the ring of the limbus is fixed.
And whole cornea is the one neurological region.
Sorry?
All material properties are the same.
No, there's a variation from the anterior surface to the posterior.
Periphery.
From a top view of the cornea, if you look at the cornea from here, they are homogeneous. Okay. But if we look at the thickness they are heterogeneous, and the posterior surface is a 50% softer than the anterior.
Okay, thank you. So exactly, it's not a membrane as the balloon.
No, it's not a membrane.
No.
It's a 3D full...
Balloon was only an example.
Okay.
But also anisotropic, right?
Yes, it's also anisotropic, yeah, with the fibers and so on and everything.
Okay.
Hello.
Hi. At the beginning of the presentation, you said that keratoconus, sorry, I'm new in the field, origin is still unknown, but from my company, more experienced colleagues, they told me that there is a clear correlation between progressed myopia and keratoconus. So that would, is this correlation are confirmed, or because that would explain somehow origin of this disease?
I don't know about that. To be honest, I don't know if it's correlated or not. But what I meant is that, like, the triggering cause from, let's say, a biological, biochemical point of view. Let's say, for example, if the concentration of hormones increase, or what is the triggering cause, I mean, the progression of myopia is something that is changing the structure of the eye, for sure, but what I don't know, or other people maybe also don't know, what is the element in the tissue that is initiating the growth, from let's say from a cellular point of view. Thank you.
Any other questions?
So my question is, can this approach help in understanding the form-first keratoconus if you combine with the optical modeling? I don't know. Can you comment on that? What do you think?
The point that is missing in this model, and it's kind of related to the previous answer, is that what triggers the degradation. This, let's say, the limitation is also that we are triggering the degradation. I mean, I trigger the degradation in the model, then it grows as it wants if there is the degradation. So I don't know now if it's possible to apply. I don't think now it's possible to apply to form-first keratoconus because it's still missing that small part of what causes this degradation, you know.
Okay, it seems there's no more question. I have a sort of one. Sorry. Which variable are you representing when you show the pictures or the evolution of the growth? You talk about growth, but what physical variable are you representing there?
With physical variable,
yeah,
in the maps,
yeah,
the pachymetry, the change in the pachymetry, that is the change in the thickness that reduces, even if it's like, wait 1 second.
I mean the previous one.
Ah, okay,
no,
here.
The previous one. There.
Okay,
It's between
I
1
call
to
this growth. Basically, this is more from continuum mechanics, so it's the growth component of the deformation gradient. But to avoid the confusion, I just called it growth. That is where the tissue is growing, basically.
Okay, it's a specific component of it?
Yeah, it's a specific component of the degradation gradient, deformation gradient, that is also everything explained in the paper, because it's more related to solid mechanics.
Okay, perfect. Thank you very much.
But it's a result, not the assumption.
Sorry?
This parameter is a result, not the assumption.
No, this is the result. Yeah, this is what the model, the result of the model.
Yeah, it's a measure of the deformation of the actual point of the mass. Okay, thank you very much. Let's move for the next speaker.
Let's now focus on how keratoconus is treated in the clinical setting. So, cross-linking is a photochemical reaction that aims at stiffening the cornea, and it represents one of the most common solutions to slow and stop the progression of keratoconus and corneal ectasia. And rather than only stopping the progression of keratoconus, cross-linking has been shown to induce a mild flattening of the anterior surface of the cornea. Therefore, it has been proposed that we could localize the cross-linking treatment on some region of the cornea and actually adopt it as a treatment for asymmetric refractive correction, as the irregular astigmatism that keratoconus induces. But someone even proposed cross-linking, localized cross-linking, as a possible treatment for minor to moderate myopia. And it actually would represent a very nice solution because it's very cost-effective, but at the moment it really lacks predictability. This means that we cannot, there is no actually any cross-linking treatment available today that says that a specific refractive stiffening of the cornea will induce this specific refractive correction. And therefore, we want to model it. We have to run an optical mechanical analysis of the cross-linking to understand the relationship between the stiffening and the induced flattening of the cornea. And what has been done in the literature is to extensively characterize the stiffening effect of cross-linking with different mechanical testing methods. But none of this focused the attention, because it's intrinsically not possible, on the refractive, on the consequent refractive effect. And to complement this analysis, finite element models have been proposed. And finite element models, as the one from Roy and Dubs in 2013, which is probably a landmark in this field, they can actually show the relationship between the stiffening and the refractive effect. But this model and the other ones that are proposed currently in the literature are only theoretical models and have not been calibrated nor validated against a clinical data. So here is where our project comes into play, and the aims of this project is to first develop and calibrate a predictive model of cross-linking, and then to validate this model in a clinical scenario. So this is the model. It's a hyperelastic model from the HGO, Old-Zaffer gas and Olden formulation. It has two different components, one for the matrix contribution of the extracellular matrix and one from the fibers contribution. It also has a viscoelastic component to better characterize the corneal behavior. The fibers have been implemented following the behavior described by Nick with X-ray scattering data, and the dispersion of the fibers through the corneal thickness has been modeled as more anisotropic on the anterior portion of the cornea and more aligned on the posterior one, according to the findings of Abbas. This is how we model cross-linking. So cross-linking is a stiffening effect that acts on the anterior surface of the cornea and then slowly decreases until 300 microns, whereas where cross-linking has been not to be effective in the clinical setting. So this is a pretty complicated model, and it depends on several mechanical parameters. So the first question was, how do we calibrate the model? How do we choose which mechanical parameters to include into the model? So what we did is experimentally characterize cross-linking, and we start with human donor corneas. We place them in an anterior chamber. We pressurize them. Firstly, we ran nano-indentation when the cornea was pressurized. Then we moved this below an OCT camera system, and we ran optical coherence elastography inflation tests. We then cross-linked half of the cornea in order to leave the other half as a control, and we repeated the experiment on the cross-link cornea, so nano-indentation and inflation. So basically now we have experimental data, we have the model. What we want to do is calibrate it, so we fit the, so there would be something that didn't happen, but we fit the experimental results of the model with our, so our experimental results with our model. The model is the black dot line that you see here. You can see the experimental results showing how the cross-linking curves is stiffer as we expect. It also has let's say a lower creep, which means that the viscoelastic behavior in cross-linking is reduced. And this is how our model fit the experimental result, and this means that the model was almost always capturing the experimental data. This is the mechanical properties that we found, and we use the nano-indentation as a calibration and the OCE as a validation of this data. These are the experimental results of the OCE, and this is how the model fits them. So it's very good in predicting the pre-cross-linking. The post-cross-linking goes a little bit onto the standard deviation of the experimental data. And this is an example of what I just said. So these are our pre-cross-linking imaging data. So the OCE data on the left is just a cross-section of a 3D model, and here is the model on the right, before and after the surgery. So we're very happy. We have the model, we calibrated on experimental data. Now we want to approach a clinical setting. Let me explain our pipeline. So we start from clinical topographies, basically the pentacam, anterior and posterior surface of the cornea. We include them in a G-mesh pipeline, so in Python, and this is before meshed and then simulated in FEBio. These are both open source softwares. This is for the meshing, and for the FE solver is also open source. The boundary condition are sliding, boundary condition applied on these regions of the cornea, and the cornea is pre-stretched, so we retrieve the pre-stretched geometry before applying the cross-linking. And we test 20 patients that underwent localized cross-linking, and of these 20 patients, 17 of them had a 6 months follow-up, so a pentacam measurement before the treatment and 6 month follow-up. Our idea is to try to replicate with our model the refractive correction that cross-linking induced at the follow-up. And this is how we model the cross-linking. Basically, this is the corneal topography. The cross-linking was applied in the clinical setting as a very high-intensity protocol in the region of the cone, and then a less energetic protocol in a 9 millimeters region around it. We have everything we need, but we actually miss a piece of the puzzle, because these are keratoconus patients, and keratoconus, as we heard before, weakens the cornea, and we don't know this. We don't know how much it weakens the cornea. We didn't get it from our experimental results, experimental work, of course. So what we did is we tried to measure this weakening in vivo with our OCE setup. It's an ambient pressure modulated setup. This means that we induce a slight inflation of the cornea, and we acquire OCT images before and after it. And we try to measure the weakening in the conical region. We did this on a subset of 3 patients. It's a very preliminary result. But what we acquired from this is actually a promising data, because we quantified a 57 weakening, which is in accordance with the literature that tested keratoconus corneas on uniaxial tensile test with brilliant microscopy, and also with the computational model that Benedetta showed in the previous talk. So now we have everything we need, and we can go to the results. This tells us, these are the pre-cross-linking results. They just tell us how the model is matching the geometry of the data, so how the model is actually accurate in reproducing the pre-treatment geometry. When we have a look at the posterior, so at this follow-up results, we can see how the model is actually very nicely correlating with the posterior curvature, with the anterior curvature of the post-cross-linking data. And if we have a look at the refractive correction, so the difference between the post and the pre-condition, the model is less good, but still nicely correlating with the clinical data. And this is an example on 3 patients of what I'm just saying. So on the left, we have the pre-cross-linking topography, the 6 months follow-up topography, and our FAM results, which on the cone seems to be accurate, and it seems also to induce a slight steepening of the cornea outside the cone region, and this is probably due to the simulation we are performing. So these are the results of our study. Of course, it's not free of limitations. The first one is that IOP was not available for these patients. So what we did is applying 15 millimeters of mercury to all of them. The second is that the model was calibrated on all healthy donor corneas, but we actually tested young keratoconus patients. So they were softer corneas because they were younger and they were affected by the treatment. And the in vivo measurement was only performed on a subset of 3 patients. But the second limitation is something we cannot really address. At least in Switzerland, it's very difficult to find keratoconus cornea, human keratoconus corneas for experimental tests. But we try to address the other 2 because these 2 are parameters of the model, and we can see how the model is affected by the changes in these 2 parameters. So if we run a sensitivity analysis, this is basically the output of almost 200 simulation. The working point of this work is this, so 15 millimeters of mercury and 40 something of the keratoconus variable, but we can see and we can appreciate how high IOP, for example, and low keratoconus factor, so a very weak cornea with high pressure, will have almost 20% more refractive correction with this approach. So this is something that has to be considered when evaluating the results of our model. So to conclude, we developed a fully automatic cross-linking model that entirely relies on open source software. We accurately, or let's say we try to accurately measure the weakening induced by keratoconus in vivo with OCE, and our model tried to accurately match the anterior surface at the 6 months follow-up. And this is the end of the presentation.
Thank you very much, Matteo. Are there any questions? Yeah, here.
Thank you very much. So I had a question regarding you said that you validated your model with respect to nano-intendation, right?
We validated with respect to the inflation, we calibrated on the nano-indentation.
You calibrate, but nano-intendation only probably probes the properties of the surface, right?
Absolutely.
Yes. Okay.
So let's be more precise. I didn't have time here. So the properties that you see here. So I don't know. You don't see probably these are actually another color scale, but these properties here were already been calibrated and developed in our group with uniaxial tensile test, done at different thicknesses of the cornea. So the model is also depth dependent, and there is this is basically the fiber components in the anterior surface, and this degrades until the posterior surface by I think 32% factor. So these are the starting properties of the cornea. We use an indentation to because it's very nice to assess the viscoelasticity. So these factors are the viscoelastic properties of the cornea and the cross-linking effect, which anyway happens in the anterior surface in the anterior region. We were not happy with it because we knew that was a limitation. So this is why we also performed the DOC inflation to see if that calibration was validated in a more, let's say, biaxial deformation, like the inflation test.
Thank you.
Thank you. Did you consider the dehydration of the tissue during the experiment? We know that cross-linking with riboflavin and UV causes the tissue to dehydrate, which is likely not a permanent phenomenon, but is a transient. Did you consider this in your experiment? Did you notice that the tissue was shrinking more than the untreated?
So what we did to try to avoid this, and we tried to avoid this the much we could, but probably we couldn't avoid at all, is so the nano-indentation system you see here is actually, we built an in-house chamber where we place the anterior chamber. So the anterior chamber is placed in a bigger chamber, which is 3D printed and filled with dextran, so an dextran solution. So actually the tissue is always in a bath during the all-line indentation measurement. We only remove that during the cross-linking, but then we repeat the measurement the day after. So we do the cross-linking, then we leave the cornea in a bath for one night, and the next morning we repeat the experiment. And of course, during the treatment you have dehydration. We hope that this approach really stabilizes the dehydration of the tissue, even we realize it doesn't at all. We don't have a significant difference between the thickness before and after the treatment, but we have a change.
Okay, and may I ask the molecular weight of the dextran?
It was a 15% concentration. I don't remember the molecular weight. It's a very, I don't know.
You get different sizes in the big ones.
Yes.
Any other questions? Okay, so we leave it here. Thank you, Matteo.
Good afternoon, everyone. I'm Saeed, an early stage researcher at Oberon, and now I study in Beroscope University of Science and Technology, and my supervisors are Professor Asishik and Dr. Milad Salimibani. Today I want to talk about a multidisciplinary study about the optical point of view about the eye glove and biomechanical aspects. At first, I want to talk about the problem definition. After that, we have some background on the third part of my presentation, the model and finite element method. The fourth part is optobiomechanical aspects, and eventually we have results and conclusion. Although eye tissues' material properties actually influence their optical performance, this relationship is unclear yet. Actually, three-dimensional eye models have rarely investigated to show the relationship between the optical point of view and biomechanical together. Material modification have been made to the cornea in our model to have to see the correlation between the optical point of view and biomechanical point of view for cornea, limbus, lens, and zonulus. And it combines physics, optometry, ophthalmology, and even biomechanics to answer this ambiguous relationship. And it may provide insights into some diseases like myopia, actually myopia, keratoconus, and even glaucoma. Let's see the background. In 2020, actually, Zetkovich et al. Shows that the wave speed of the limbus is between the cornea and sclera at IOP is equal to 15 milliliter per mercury and rapidly increased as IOP was raised. And the limbus shown that the limbus actually behavior highly nonlinear. And also they said that the limbus have enough structural flexibility to stabilize anterior eye shape during IOP change. In 2020, Fayem et al. Talked about the limbus stroma and posterior limbus, and they mentioned that these two parts are so important regions of the cornea. And also in 2023, Shahir et al. Talked about optomechanical self-adjustment standard and emphasis managing the eye borders and peripheral, and emphasis that the limbus geometry influence on actually optical parameters. But in our model, we considered a 3D model of human eye. You can see here a model. A 3D model of human eye includes sclera, limbus, zonulus, lens, and also for our boundary condition, extraocular tissue, we consider viscoelastic Kelvin-White model. And the limbus is a separated radiological area that you can see in the middle part of the model. But what about the method? In the follow, if you can see, our investigation divided to 3 steps. The first step is the 3D model generation. After importing our model to FE software, we should assign a material model to all parts of our eye glove. For corneal, limbus, lens, and zonulus, we consider hyperelastic neo-Hookean model. For sclera, we consider Yeo model. And draw abacus FEM software, meshing algorithms we used. We actually had around 50,000 hexahedral elements on all eye glove model. And in the sclera, spring and dash spots are symmetrically distributed, applied in 4 points in the outer layer of the sclera. And we considered IOP between 16 to 28 millimeter per mercury in both anterior and posterior chambers equivalent. And one of the most important parts of our investigation was optobiomechanical aspects. By keeping the remainder constant, each parameter's initial properties have been modified, and C10 is a parameter of neo-Hookean model that is related to the Young modulus and Poisson's ratio. We changed it quarter and 4 times of initial material properties of limbus. And as you can see in this figure in the left side, in accordance with this figure, which represented the item analysis between different 5 parameters of eye geometry, CCT, R1, R2, VCD, and ACD. Results show that the limbus material properties is the most crucial to effect on optical parameters. So, actually, terms X and Q in the figure shows that, terms X and Q in the figure shows the 4 times and quarter times of initial material properties of limbus. So at the end, we consider 4x initial material properties of limbus is the most important part to change effects on optical parameters. After that, we focus on the material properties of limbus and change 10% from the initial material properties of limbus until 4 times of initial material properties of limbus to show the effects on the optical parameters. And let's look at some results here. if we consider the focus as criteria for image quality, we have minus and plus 0.07 millimeter of the focus. It's equal to refractive error less than 0.25 diopters. And this chart shows that when we change the material properties of limbus, you can see here the percentage of increase in limbus stiffness. We have a nonlinear decrease trend when we increase the stiffness of limbus. And if we consider just the focus as a criteria, we have a range between 2.6 times of limbus material properties until 6 times of limbus material properties, that we have a good vision with a small refractive error. Another result is about the R1 and versus material properties of limbus. Again, we have nonlinear decreased trend for all intraocular pressure, 16 to 28 millimeter per mercury. Another result is about the VCD and ACD. You can see here for ACD, when we increase the material properties of limbus, we have nonlinear increased trend in ACD anterior chamber depth. But for the VCD, we can see a nonlinear exponential decay trend, as you can see in the right side of the slide. What about the displacement? For IOP is equal to 22 millimeter per mercury, and thermodix means the multiplier of initial material properties of limbus. In initial material properties of limbus 2 times, 3 times, 4 times, 8 times, and 10 times. By increasing the properties of limbus, actually C10 as I mentioned before, the displacement of the lens and cornea decreases, and the displacement of the sclera is actually almost constant, and with the increase of the distance from the limbus, the displacement on the sclera is negligible. So you can see here in the photo for the sclera. So the most important part of the displacement when we increase the material properties of limbus at 22 millimeter per mercury is the lens after that cornea. Another result is about the strain at 3 times of initial limbus material properties for 16 to 26 millimeter per mercury. Stress concentration on the zonuolus is the most, so we can see the most strain on this part. Softest part of the eye glove actually is the zonuolus, as you know, and one can see that limbus and sclera connected to the zonuolus have more homogeneous strain as IOP increase. This one. And what about the stress? For IOP 20 millimeter per mercury, again for initial material properties of limbus until 8 times of that. From mechanical perspective, greater mechanical properties of limbus is required in order to achieve a more uniform tangent, but we have a problem when we didn't consider optical point of view. So limbus is look like a ring look like a ring around the cornea, and limbus controls the shape of the cornea, especially the central part of that. And important for vision also, it's important to change the corneal stress, and we can see here a pattern that is faded when we increase the material properties of limbus. And stress distribution for 16 to 28 millimeter per mercury for initial material properties of limbus, and 2 times and 3 times of initial material properties of limbus. If you can see in the photos for red lines area, there is a transmission of tension from the endothelium layer to the epithelium layer as intraocular pressure increased, and a stiffer limbus decreases actually the tension on the endothelium layer and making the cornea appear more homogeneously. And in order to have more homogeneous scleral limbus and corneal section. Another part that is important in the yellow line is the limbus. And for the limbus, considering the fixed stiffness for these charts, the limbus, and with increased intraocular pressure, the tension along the thickness of the limbus is stressed first from the area connected to the cornea. If we consider for the constant material properties, this analysis is the same. And to conclude, based on the analysis between the 5 geometrical parameters of the eye and change in the material properties of different eye parts, the properties of the limbus are the most crucial. Compromise between geometrical parameters and material properties to obtain the focus limit between plus and minus 0.007. The most displacement occurs due to the change in the properties of limbus on the lens and then on the cornea. With the increase in IOP, the strain of the zonulus, the area connected to the lens, increased greatly. This could be because of the zonulus has almost the softest property. And with the stiffer limbus, the endothelium layer is less stressed through the corneal cross-section. And at the end, an eyewall's limbus is a ring-shaped structure that controls the shape of the cornea, especially the central part. Not only does it have an effect on the vision, but it is also important to change corneal stress. Thank you so much for your attention.
Okay, thank you, Saeed. We have time for quick questions. Barbara?
Thanks, Saeed. I have a few, but I'm only going to ask you the one. So you talked about the effect on the zonule, the increase in pressure. If you just go to your last conclude, the slide before this one, I just want to make sure I've understood you correctly. Yeah, the fourth point. So, if that increase in intraocular pressure so affects the zonule, then it would have an impact on accommodation, and vice versa. Accommodation should have an influence on the changes in IOP as well. We don't really see that clinically, so I'm not quite sure when you say increases greatly, what that greatly means.
Actually, because of the amount of the displacement, I mentioned this, but zonulus for the actually Neo-Hookean model from the previous research, it's the softest property than sclera, than cornea, limbus, and even lens. But maybe the greatly it's not mentioned here.
Yeah, maybe there are other tissues surrounding the zonules that have not been considered in the study, right?
Yeah.
For instance, the muscle. It was considered the muscle in your model?
Actually, we consider viscoelastic model as a Kelvin Voigt viscoelastic model. It needs to have a stiffness and dashpot parameter. For dashpot, we consider previous research, use the amount of the previous research. For the stiffness, we consider the truss element. A divided to L is Young modulus. A is this cross-section area that the element work on, and L is the thickness of the fatty tissue.
Okay, any other question? Okay, thank you, Saeed.
Thank you.
Let's move to the next speaker, Vahoura Tahsini from the University of Bern.
Okay, hello everyone. My name is Vahoura. I am PhD researcher of the University of Bern, Switzerland. My presentation topic is about porcine sclera biomechanics using uniaxial extensometry combined with optical coherence elastography. Apart from the important role of cornea and crystalline lens, which is important for creating image on the retina, sclera is also important in maintaining ocular size and refraction, maintaining intraocular pressure, and protecting the internal ocular structure. So, sclera has the weaknesses and problems in the sclera can create some problems in the ocular system, like refractive error of myopia, which is related to the elongated posterior scleral shell, and also glaucoma, which is related to the damage to the optical nerve, which can be related to the weakness of the sclera. Apart from this problem, the individual differences in mechanical properties of sclera and also increasing scleral stiffness with age made researchers to work on the sclera biomechanics to have a better understanding about the sclera, about the disease origin and its progression, and also to have accurate prediction of surgical outcomes. So because of that, a lot of research has been done by now, like using indentation technique, using inflation, and also using uniaxial and biaxial tensile tests for assessment the biomechanical properties of the sclera and cornea and whatever tissue of ocular system. But a weakness that this technique has, the mechanical properties of this kind of technique differs largely together, and also there is not much information about the orthogonal direction of the sclera. And also apart from that, there is two important techniques that is used for assessment the biomechanical properties of sclera, like ultrasound technique and also optical coherence elastography as a high resolution technique. So for our experiment, we use optical coherence elastography for assessment the mechanical properties of the sclera. For this purpose, we used laboratory-based optical coherence tomography setup with axial and lateral resolution of 3.3 and 14 micrometer. And also for the mechanical stimulator, we used uniaxial tensile system with different range of preload and stretching rate. And we combine these two methods together to have a full optical coherence elastography method. So the process of this experiment is we are connecting the sclera flap to the uniaxial clamp, and we are stretching that. And at the same time, we are imaging of the sclera by optical coherence tomography system. And then we are analyzing the signal. So for the signal processing, actually two cross-correlation B-scan is generated for assessment, firstly the displacement of the tissue, and after that for assessment the phase difference of the signal of the two subsequent B-scans. So the advantage of optical coherence elastography is there is not dependency on the refractive index of the tissue. So our test condition was based on using 18 sclera flap with dimension of 2 mm times 1.2 millimeter. We used 6 subsequent loading and unloading cycles with a stretch rate of 5% under different preloads. And for the optical coherence tomography, we used 250 subsequent B-scan for imaging of the sclera at the same time that we are stretching the tissue. And the overall test duration lasts 5 minutes. So about the results, apart from having a high resolution strain map of the sclera by using optical coherence elastography technique, the important thing that we noticed during the experiment and analysis of the signal, we noticed that in low preload, with increasing the lateral strain by using uniaxial system, we had negative axial strain, while in the high periload with increasing lateral strain, we had positive axial strain of the tissue, which is showing with expansion the tissue in x-axis, we had expansion in z-axis in the direction of optical coherence tomography system. But actually we didn't measure the deformation of the tissue in y-axis. Overall, with this experiment we can assess the Poisson ratio of the tissue by using this technique, which with this experiment we could measure that in the low preload, the negative Poisson ratio was lower than the high preload. And so with this technique, we could get that the positive axial strain could imply of auxetic behavior of the sclera, or the lateral shrinkage in third dimension, or it can be related to the osmotic diffusion of the sclera. The limitation of this technique can be related to the flat cutting and the uniaxial loading test, which was under unnatural condition. And also strain in the third dimension has not been measured, as I told you. And for the outlook, in parallel, we are working on the using inflation interior chamber with connection to the optical coherence tomography for whole parts of the cornea. For a conclusion, I need to say that for the first time, we could simultaneously measure the transversal and axial strain of the sclera by using uniaxial tensile system and optical coherence elastography. The combination of optical coherence elastography and uniaxial extensometry is a suitable way for having a comprehensive strain assessment. And the mechanical response of the sclera in loading forces within the physiological range was different with the loading forces outside of the range of physiological. And thank you so much for your attention.
Thank you, Vahoura. Questions? Over there.
Thank you for your presentation. I was just curious, what was the repeatability of your measurements? Because there were like 18 probes there, but on the graph on the plot I couldn't see if they are similar, all of them, and also I'm curious if you did this experiment just like one day for all of the probes, or did you control somehow those?
Yes. Actually, what I did, we used 6 sclera, and we got this from the optical network. It was 6 sclera that we used, and we used dextran solution. We put in the dextran solution, and no, we used actually in first pay that we bought the eye from the slaughterhouse. But yes, exactly, we should have more experiment to be more precise. And I can tell you that this is not the end of the story, because we should repeat this test, and we should repeat this test for whole part of cornea, and whole part of sclera in the interior chamber, actually, to see that this cutting the sclera can influence on the results or not.
Thank you. It's always challenging, yeah?
Yeah.
So to repeat it in the
Yes,
same way.
exactly.
Thank you.
Following the previous question, so we also observed in the cornea if you have some kind of inflation test, so depending on how many numbers, it's just the response is different. So, but this is for cornea. I don't know how it works for the sclera. So we need to keep this in mind also.
Okay, thank you. Thank you.
Thank you. Any other questions? Okay, you have mentioned that maybe cutting the sclera will influence to the behavior.
Yeah.
Do you have some ideas on how this would be?
Maybe the change in the fiber orientation, fiber direction can influence on this, and also probably the absorption of, because we are putting the tissue in the dextron, and maybe during the test the absorption of the tissue by dextron can influence on the osmotic behavior of the tissue, and it is influencing us by mechanical properties. But this is hypothesis. We should repeat them.
Yeah, certainly. It was quite, quite weird for me seeing a Poisson ratio that is very low in those cases. So maybe you're right, something is happening,
yes.
Some interaction between the fluid and the fibers or the canals that can be formed when you cut the sample. So, okay, thank you very much.
Good afternoon, everyone. My name is Elena Redaelli. I'm from the University of Zaragoza. And to introduce the problem, I would like to show you some images. The majority of us would see this landscape clearly. But if one of us is affected by keratoconus, the pathology explained in the previous presentation, the same landscape would be blurred and distorted. In case of glaucoma, the landscape would appear with the tulle-like effect because glaucoma pathology causes the loss of peripheral vision. In case of many of us affected by myopia, the vision of distant object would be blurred. So I'm here today to explain which are the advancements we made in the field of corneal biomechanics in order to address these pathologies and to relate the corneal biomechanics to the prevention of corneal pathologies. So we all know that the cornea is the primary refractive surface of the eye, and we are interested in the mechanical properties of the corneal tissue. The cornea is an anisotropic tissue, that means that it is composed of collagen fibers, and the mechanical behavior at low deformations is different from the mechanical behavior at high deformation because it has a non-linear behavior. Moreover, the behavior in the direction of the fiber is different from the behavior in the perpendicular direction. One important remark is that the corneal biomechanics is not only composed, the study of the corneal biomechanics is not only composed by the study of the mechanical properties of the corneal tissue, but it includes a complex interaction between a lot of factors that are, yes, the mechanical properties of the corneal tissue, but also, for example, the intraocular pressure, the geometry of the cornea, any external load acting on the corneal surface. So today, one slide is missing, but today, okay, this is. Today our question is it possible to estimate the mechanical properties of the corneal tissue from the results of a non-contact tonometry? The non-contact tonometry is a non-invasive, a non-invasive diagnostic tool intended to characterize the corneal biomechanics, so the complex interaction between all the factors. And our aim is to decouple all the factors and estimate in real time the mechanical properties of the corneal tissue in vivo. So, what we did was, first of all, to create a finite time element model of this clinical test. I'm not going into the detail, all the details of this finite element model, but you can find everything in the paper in the QR code. Basically, it is a fluid structure interaction simulation That means that we have a structural part that is composed by the cornea, limbus, sclera, and humors. The cornea is a patient-specific corneal model because it is based on pentacle data of patients. And the material model we used to describe the corneal behavior is an anisotropic model. This anisotropic model we have chosen depends on three parameters that are called C10, K1, and K2. C10 describes the behavior at low deformations, and K1 and K2 accounts for the influence of the collagen fibers, so the behavior at high deformation. I said that we have a fluid structure interaction simulation, so we have also a fluid part. The fluid part is the air impacting the eye during the non-contact tonometry, and the air is modeled as an incompressible fluid with a proper density and dynamic viscosity. So these are the results of our simulation. We have a first step that is a pressurization of the eye from the zero pressure configuration we properly found through an iterative algorithm, and then the deformation of the eye thanks to the air and structure interaction. The main problem of this simulation is the high computational cost. Only the running time of one simulation is 48 hours. So it is possible to implement this simulation in clinics in real time. For this reason, we created a large data set of simulations. So the same simulation, we repeated it with a lot of different input parameters. The input parameters are the geometry, so different patients with different Zernicke approximation, the intraocular pressure, and the mechanical properties of the corneal tissue. For each simulation, we recorded the deformation of the cornea in the central section. That is the same section that Corbis in clinics reports. With this large data set of numerical result, we decided to reduce the dimensionality of the problem. We used this technique that is called proper orthogonal decomposition, in which the results are approximated by a basis, and we have chosen a reduced basis that is able to describe the 99% of the model. In our case, only 8 bases are sufficient to describe all the 99% of the variability of the model. You can see the difference here between the simulated results in red and the results when using only 8 bases, so the reduced model in blue. Since the difference is basically inexistent, we can say that this reduction of the model can be used for future analysis. It is important to state that the basis we found is the same for all the simulation we run. So the basis is not dependent on the inputs of the simulation. So we need to compute some coefficients which, multiplied by the basis, can give us the corneal displacement during the air path. We used these coefficients together with the intraocular pressure that was the input of our simulation and the Zernicke coefficients describing the anterior and posterior surfaces of the cornea to train an artificial neural network. The output of this artificial neural network are the 3 parameters describing the mechanical properties of the corneal tissue. When training an artificial neural network, usually the data are divided into train and test cases, and the test cases are not used during the training. So these are the results when using the test data, and we can say that using this test data, the mechanical response of the corneal tissue simulated, that is the one we used in the simulations, and the mechanical response of the corneal tissue predicted by the artificial neural network are the same, and this proves the reliability of our neural network. Okay, we created this complex model, but how can we use it in clinics? In clinics, we have the images from Corvis ST. And we would like to have, for this particular patient, the mechanical response of the corneal tissue. First of all, the first step is to parameterize the corneal surface, but it's simple. From the pentacam data, we can find the Zernike coefficients describing the corneal surface. Then we need the IOP, and for this step we published recently a paper in which, from the results of the non-contact tonometry, we propose this formula to estimate the intraocular pressure independently on the mechanical properties of the corneal tissue. And the idea behind this methodology is to base the estimation of the IOP on the time of maximum velocity of the apex, rather than the time of first applanation of the cornea. Okay, the third step, once we have the IOP, is to segment all the images, and this is only a plot to show that the segmentation was validated, and we used this segmentation of the images of Corvis ST to compute for that particular patient the coefficients that multiplied by the basis, by the reduced basis, give us the corneal displacement. So these four steps gave us the Zernike coefficients, the IOP, and the reduced basis coefficients, which can be given as input to our artificial neural network model, and this model estimates in real time the mechanical response of the corneal tissue. Of course, we created an algorithm to perform these 6 steps, and the algorithm takes less than 50 seconds to estimate the mechanical properties of the corneal tissue in vivo from the images of Corvis ST. So this is the application of our methodology, and since it is real time, we hope it can be implemented without any problem in the Corvis ST device, and in this way we can have a deeper knowledge on the mechanical properties of the corneal tissue in vivo. So I would like to thank my team, the project who found this work, and all of you for your attention. If you have any question, I'm here.
Thank you, Elena. You have stolen this picture. Any questions?
Hi. I wonder how better understanding of mechanical properties of corneal tissue can help prevent glaucoma.
In glaucoma, the main problem is that, for what I understood, is that we don't know that the pathology is raising until the patient has any problems. I mean, when the optic nerve is damaged, it's too late to treat the pathology. So it is important to have a good knowledge of the value of the intraocular pressure in order to prevent the damage of the optic nerve. And if we don't know the mechanical properties of the corneal tissue and they are related to the intraocular pressure, this can be a problem because in case of the non-contact tonometry, for example, if we have a high intraocular pressure and we don't know the mechanical properties of the corneal tissue, we can have misunderstanding in that.
Okay, so which symptoms of the pressure can indicate that the patient may have glaucoma?
I'm not I'm not sure, but I think that higher than 20 millimeter of mercury can be a symptom of glaucoma, but I'm an engineer, not...
That's okay, thank you.
Thank you.
I'm not really sure if the term real time is correct in this case, because real time means that you can do that quickly with repeated measurements, but in case of AirPuff study, we don't do this so quickly in patients. So can you comment on that? I would say it's nice to have this information very fast, right, after the measurement, but in clinical practice, you just do that once and then we obtain the result.
Yeah, real time was referring to the computation, to the estimation of the mechanical property, not to the process before the estimation. I mean, we should have the clinical results, and but if we implement this model in the clinical device, during the clinical test you have the information of the mechanical properties. So in that sense, real time.
But 50 seconds compared to 48 hours is probably nearly real.
I mean, usually real time indicates that you repeat something and you have like real time display, for example, right? But in this case, you do this test like once only, and of course, having the result very fast is okay. Is very good.
Yeah. So this is something.
But this is not really. This is what I would think.
Yeah, this is something that for the non-biomechanical people has not been mentioned along this presentation. The time that our models takes to provide good results, and all the effort that is behind all those models that probably here in this short presentation is impossible to show to us. Okay, are there a couple of questions there?
Yeah, one question, because in your model, I've seen that you assumed there is no iris and no lens. And how do you see it? May this anterior chamber depth influence the process of corneal applanation? And how do you see it? How to include it in the model?
Okay, in this paper, in this QR code, I included also the crystalline lens in the model, and then I studied the influence of the presence of these structures on the results I was interested in, that were the displacement of the corneal surface. And since in this particular case they are not influencing the results, I decided to remove them for a matter of computational time. But yet, if we are interested in other results, they should influence.
Okay, thank you.
Just a short question. There were a few slides. If you go back a few slides, there were some plots of indices, and I didn't see the units.
Which one?
The red plots.
This one.
No, back. Back. Oh no, probably at it was at the end. Almost at the end.
Okay.
Sure. So yeah. So what are the units of this?
They are unitless because the units are in the basis, and the bases have the unit of millimeters, and multiplied by these coefficients, we have displacements.
And I've got another question, because as far as I know, the Corbis ST software already enables some mechanical properties, also including this Vinci-Guerra statistics and so on. So maybe I missed it somewhere, but what is like the biggest advantage or on your model comparing to the existing solution?
Yeah, the idea behind that index was to consider the mechanical properties of the corneal tissue always with the same shape. So the numerical model used to estimate that parameter was not including the anisotropicity of the cornea. And since here we are including the anisotropicity of the cornea, the model is more detailed, and moreover, that index gives us one coefficient. It's one index, and so it says us, okay, we can modulate this same curve based on the displacement we have. Instead, in this case, as you can see here, we can have different behavior depending on the deformation. So we can have a more deformed cornea at low deformation and stiffer cornea at high deformation, and the shape can be different.
And did you compare it somehow to those existing properties?
Yes, yeah, and but since I compared only one patient, I can't conclude something. Yeah, it's a future work.
Thank you very much.
Okay, so thank you, Elena.